Hello everyone and welcome to optimization tutorials in Python. In these tutorials, we provide real and applicable knowledge of optimization, applied mathematics, control theory, signal processing, and machine learning. This particular tutorial is dedicated to the problem of solving systems of nonlinear equations in Python by using the FSOLVE Python function and by specifying the Jacobian matrix of the nonlinear system. In my previous tutorial, whose link can be found in the description below this video, I explained how to solve a system of nonlinear equations in Python without specifying the Jacobian matrix. The advantage of specifying the Jacobian matrix is that we can significantly speed up the convergence of the nonlinear solution method that's used for solving nonlinear equations. That is, by directly coding the analytical form of the Jacobian, we can obtain a very fast solution. This is especially important for nonlinear equations with a large number of unknown variables. If we have a large number of unknown variables, the convergence can be sometimes very slow. Then, if we can find the Jacobian of our nonlinear system of equations, we can code this Jacobian and we can significantly speed up the convergence. And that's the main motivation for creating this video tutorial and for teaching you how to directly code the Jacobian matrix. So, the take-home message is the following. If you can analytically compute the Jacobian, always do that and code that Jacobian. You will be able to obtain a very fast solution. Before I start, I would like to mention a few important things. Those of you who are my subscribers or who follow this channel know by now that I always create a post that nicely summarizes everything that I will explain in this video, and consequently here is the post. This post contains all the explanations, equations, and Python codes. A link to this post is given in the description below. Secondly, it took me a significant amount of time, energy, and planning to create this post and this video. And consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, let's start. The function FSOLVE can only solve square systems of nonlinear equations. That is, the number of unknown variables has to be equal to the number of equations in the system. Then, according to this documentation that you can find by accessing this link, you can read that actually this function is a wrapper for the hybrid Powell method that's implemented in the Fortran 90 library called minpack. And you can read more about this library by clicking on the link. And here is the description of the implemented algorithm. Again, this is very useful information if you're writing a scientific paper or if you want to cite the literature. In my next tutorial, I will explain how to solve underdetermined or overdetermined systems of nonlinear equations. Okay. To explain you how to solve systems of nonlinear equations, I constructed a test case given over here. These are three nonlinear equations with three unknowns, x, y, and z. And I constructed the system such that I know the exact solution. And here's the solution: x is equal to 1, y is equal to 1, and y is equal to 2, and z is equal to 3. And you can verify that this is actually the solution by substituting these values in the original system. And if you substitute the values, you will obtain that zeros are equal to zeros. That is, the left-hand sides are equal to right-hand sides, and everything is perfect. However, while solving these systems and while testing my Python code, I realized that there is another solution, and this another solution is given over here. So depending on your initial guess, you will obtain either the solution x is equal to 1, y is equal to 2, and z is equal to 3, or the solution that you can see over here. So keep in mind this thing while testing the code. The first step when solving this system in Python is to introduce a new set of variables. I will introduce variables w0, w1, and w2 that will be equal to x, y, and z respectively. I'm introducing these new variables since I want to implement a function in Python. And another thing to keep in mind is that I'm starting indexes, or better to say indices of variables from 0. I'm doing that in order to be consistent with Python notation. The next step is to write our original system of equations given over here in an appropriate form, that is, in the vector form. Here I will explain you how to transform the system in the appropriate form. As I mentioned previously, I'm introducing new variables. Next, I will substitute these variables in the original system, and as the result I will obtain this system. This is the first equation, this is the second equation, and this is the third equation. Here it's always a good practice to stop and to check that you have accurately performed all the substitutions, and we can see that everything looks good. The next step is to transform this system, that is, to remove all the constants from the right hand side to the left hand side. And as the result, we obtain this system over here. Minus 15 is equal to 0. This is the first equation. The second equation is actually a linear equation, and it's given over here. And here's the third equation. Minus 6 is equal to 0. Next, we can introduce a vector w that looks like this. w0, w1, and w2. And our next goal is to write the system into the vector form that looks like this. We need to define a function f that represents the left-hand side of the original system. And obviously this function f will look like this. f0, f1, and f2, where f0, f1, and f2 will be the left-hand sides of this equation over here. So f0 will be 2w0 squared plus w1 plus w2 squared, w0 plus w1 plus 2w2 minus 9, and here I forgot minus 15, so keep in mind these things, don't forget the constants. And the third equation, or the third left hand side, looks like this. Okay, so we started from the original system in the original variables x, y, and z. We introduced new variables, we transformed the system in this form, then we additionally transformed the system by placing all the constants from the right hand side to the left hand side, then we wrote the system in the vector form that's given over here. Now when you have this vector form of the system, you can proceed with the Python implementation. The next step is to define the Jacobian matrix of the vector function f. The Jacobian matrix of the vector function f is defined as follows. Partial derivative of f with respect to the vector variable w, where w groups all the unknown variables w1, w2, and w3. This is the symbol for the Jacobian matrix. The Jacobian matrix is a matrix obtained by taking partial derivative of f with respect to the vector w. Its rows and columns are defined as follows. The first row is defined by taking the partial derivatives of f0, that is, the partial derivatives of this function, with respect to all the unknown variables. So we have in the first row delta f0, delta omega 0. Then delta f0, delta omega 1, delta f0, delta omega 2. This is the first row. The second row is defined in the similar manner. We take the nonlinear function f1 given over here and we compute the partial derivatives. And the partial derivatives are delta f1 over delta omega 0, delta f1 over delta omega 1, delta f1 over delta omega 2. And similarly, the third row is obtained by taking the partial derivatives of f2 with respect to unknown variables, and we have delta f2 with respect delta omega 0, delta f2 with respect delta omega 1, delta f2 with respect to delta w2. Notice here that I made a simple error in pronouncing W, I sometimes say omega, so please forgive me for that. Keep in mind that it's W. Okay, so this is our Jacobian matrix. If you compute the partial derivatives, you will actually obtain the Jacobian matrix given over here. Let me just explain you how I obtained this term. It's super easy. Basically, I took f0, and what is the partial derivative of f0 with respect to w0? It's nothing less than 4w0. This is because when taking partial derivatives, omega 1 and omega 2 are considered as constants. Okay, now that we have analytical form of the Jacobian matrix, we can implement the solution in Python. The first step when implementing the solution is to import all the necessary libraries. And as you can see over here, I'm using the Spider environment. Spider environment is super useful for testing Python code since it resembles MATLAB. For example, you can simply select a piece of code and you can evaluate it over here. And this is very useful for debugging your code. Okay. First, we import all the libraries, and here are the libraries. I need the NumPy library, and from SciPy Optimize, I import FSOLVE. This is our solver. Okay, I will repeat the steps. Perfect. The next step is to define the function f in Python. The function f is given over here. This function accepts w vector as an input parameter, and it will produce this vector over here. That is, it will produce the value of the function f for the input parameter w. Note here, if w is actually equal to the solution of the problem, the value of f will be equal to 0. Otherwise, if w is not the solution, f will not be equal to 0. Over here, you can see the entries of f, and you can see how I implemented these entries. I defined the function, and the name of the function is nonlinear equation. It basically first defines f vector as vector of zeros. This is the first entry of this vector, and this is the first equation given over here. The second equation is the second entry, and the second entry is given over here, and here is the third entry that's equal to the third equation. At the end, you need to return the value of f. The second step is to define a Python function that defines the Jacobian matrix. Here is the function. This function takes as an input argument W, it's a vector, and it produces the Jacobian matrix and it returns the Jacobian matrix. Here is the Jacobian matrix, and I just need to code these entries. So this is 0, 0, this is 0, 1, 0, 2, 1, 0, etc. And over here you can see how I implemented this matrix. 0, 0 is obviously 4 times omega 0, and you can see it over here. For example, let's test this entry. So this entry should be 0, 1, 2, 1. So it should be 2, 1. So let's verify this entry and let's see that it's correct. So it's W0 times W2, going back to the code, W0 times W2. After you enter all the entries, you just need to return the Jacobian matrix. When solving a system of nonlinear equations, we also need to generate an initial guess. This is because the function FSOLVE uses an iterative approach to solve the system of nonlinear equations, and consequently we need to initialize the iterative solver. Note over here that I'm using a simple random guess of the solution. However, if you have some a priori information, you can use this a priori information to generate a better initial guess. And over here, I solve my problem. I use the function FSOLVE. The first input argument of this function is my nonlinear equation, that's our f function, that's the function over here. The second argument is the initial guess. Here's how I generate the initial guess. It's a vector. The third argument is the function defining the Jacobian matrix. So I just say f prime is equal to the Jacobian matrix. Jacobian matrix is defined over here. And the last argument is this flag, full output is equal to 1. By specifying this flag, I'm saying to Python that I want to obtain the solution and all the information related to this solution. I will explain this in the sequel. So let's execute the code until here, and let's compute the solution. Okay, you can see that in a fraction of a second, we are able to obtain the solution. Let's investigate the solution. Okay, here's the solution. This variable over here, solution dictionary, is actually a tuple. The first tuple, or actually the first entry of this tuple, is the computed solution. And we can extract it like this. And if you type solution, you will obtain the solution of the problem. We can clearly see that the solution is 1, 2, 3, and that should be the correct solution. And you can compare this solution with the initial guess, and you can see that actually Python, or better to say the function FSOLVE, is doing a great job. Here is the initial guess, and here is the computed solution. Now, here's some other parameters over here that are interesting. In this initial guess, or actually in the solution dictionary, tuple, the second entry is a dictionary. And this dictionary contains a very useful information. For example, over here you can see that the solution converged. Perfect. Then you can see the residual over here. That is, you can see the value of the function f computed at the solution. To explain this better, if we substitute approximate solution over here, we should obtain a very small numbers as entries of this vector. And that's precisely the case that you can see over here. So this is the first, second, and third entries. These are very small numbers. Another important parameter is this parameter NFEV, and that's the number of function evaluations. And you can see that our algorithm converge in 18 function evaluations. If you run the same problem without specifying the Jacobian, you will obtain this result, and I'll just execute the code. You can watch my previous video that explains this code. So here is the solution info, and let's see what's happening over here. We can see that the number of function evaluations is 30, and this is very important because by specifying the Jacobian, we are able to significantly speed the convergence of the problem. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.